Historically, our approach to wastewater has been mostly passive, focusing primarily on treatment and disposal. However, the long-held goal in the field has been to shift towards carbon energy neutral processes that also facilitate the recovery of resource. This is crucial considering that over 50% of a city's lost or wasted resources can end up in its wastewater. For over a century, we have collected biogas through anaerobic digestion, and the nutrient recycling has been effectively managed through the land application of biosolids. This practice not only conserves energy but also recover resources, which are critical considerations as we expand technology based on biological sulfur conversion. Our discussion in this lecture will focus on the emerging opportunities that this technology presents. We are looking at the recovery of metal, mineral, and metabolic intermediate, such as hydrogen, hydrocarbon, and polyhydroxyalkanates. These elements are pivotal in the rapid advancement of biological sulfur conversion technologies. By embracing and incorporating these principles, we are not just treating wastewater, we are opening the door to a more sustainable future, turning waste into wealth and contributing to a circular economy. Metal sulfides are widely used in industry processes due to their unique properties, playing a crucial role in hydroprocessing in fuel refinery and oxygen reduction in fuel cells. At the nanoscale, these materials found applications in cancer therapy, photocatalysis, and as antimicrobial agents. In the petroleum refining industry, hydroprocessing involves using hydrogen gas with a catalyst to remove impurities from crude oil, making products cleaner and more valuable. Hydrocracking, a common hydroprocessing type, breaks down heavy oil fraction into lighter hydrocarbons using bifunctional catalyst, often composed of metal sulfides. Furthermore, metal sulfides are employed in batteries, notably in lithium-sulfur batteries, which are prized for their high energy density and potential cost advantages over lithium-ion batteries. These batteries use sulfur and metallic lithium to achieve higher energy density, although they face challenges like poor cycle stability and rate performance. Metal sulfides also show promise in advanced application across medicine, environmental science, and energy production due to their light adsorption, optical characteristics, and catalytic capacities. They are used in a variety of energy-related applications, including as electrode materials in various batteries, solar cells, and supercapacitors, and as catalysts for environmental remediation. Metal sulfides are typically synthesized using various methods, including high-gravity chemical baths, gamma radiation, ferrolysis, and thermolysis of metal complex, which often require high temperatures, pressures, and potentially hazardous chemicals. These traditional methods necessitate strict safety protocols. Recently, techniques such as physical vapor deposition and chemical vapor deposition have been employed to synthesize metal sulfide nanostructures at low temperatures without catalyst. And high-pressure autoclave processes are also used to facilitate the oriented growth of these nanostructures by overcoming high interfacial energy barriers. The shift towards green chemistry highlights the use of environmentally benign reducing agents and non-toxic solvents in synthesis process. Additionally, biomolecular assisted synthesis has emerged as a promising method for producing metal sulfide nanomaterials, leveraging the unique structures and self-assembly capacities of biomolecules to direct the shape and size of nanostructures. Despite advancement, many synthesis methods still involve complex, costly, and energy-intensive procedures that use expensive equipment, surfactants, catalysts, or templates. There is growing need for simpler, cost-effective, and environmentally friendly approach to produce high-yield metal cogenate nanomaterials efficiently. The biological production of metal sulfides, such as the intracellular synthesis of cadmium sulfide nanoparticles by microorganisms, presents a safer, more cost-effective, and environmentally friendly synthesis approach. Notably, the photosynthetic bacteria Rhodopseudomonas can produce intracellular calcium sulfide nanocrystals, as can E. coli did, which generate cadmium sulfide nanocrystals within the size range of 2 to 5 nanometer. These biological methods leverage the natural metabolic processes of microbes to create metal sulfides, offering a sustainable alternative to conventional chemical synthesis and opening new avenues for nanotechnology and sustainable materials development. Now let's also look at metal sulfides and their production through the metabolic pathway of sulfate-reducing bacteria. SRB play a crucial role in the reduction of sulfate to sulfide. This metabolic process results in the extracellular binding or precipitation of metal ions in solution, leading to the formation of valuable metal sulfides. As we can see from the table, various metal sulfides are produced through metabolic pathway of SRB. Metal sulfides can be produced through the metabolic process of sulfate reducing, which play a key role in converting sulfate to sulfide. This process results in extracellular binding or precipitation of metal ions, forming valuable metal sulfides. For example, copper sulfide is produced via this pathway that is utilized in various industries, including as a photothermal agent for cancer cell ablation due to its extracellular formation and operational pH of 6.0, making it suitable for medical applications. Another significant product is cadmium sulfide, a semiconductor material used in solar cells and sensors, synthesized intracellular by certain microbes. This instance illustrates the diverse and potential use of metal sulfides generated through the metabolic activity of SRB, highlighting this method as a sustainable and eco-friendly option for producing valuable metal sulfides. The application of sulfate-reducing bacteria in metal sulfide production utilizes two main strategies. One is inline system. This method involves directly introducing metal into the sulfidogenic system, where it reacts with the sulfide produced by sulfate-reducing bacteria, allowing for immediate and efficient metal sulfide production in one integrated system. The advantages are biological produced metal sulfides like zinc sulfide from disulfur vibrio are more stable than those produced abiotically. This stability is crucial for applications requiring long-term material reliability. Furthermore, biogenic nickel sulfide exhibits improved crystallinity, enhancing its industrial applicability. The disadvantages are, however, extracellular polymeric substance produced by sulfate-reducing bacteria can obstruct metal sulfide formation, and protein-induced aggregation can hinder particle dispersal and reduce yield. Another system is offline system. Here, sulfate-reducing bacteria produce sulfide separately, which is then isolated and used to precipitate metals in a different process. This approach offers flexibility and control in the production and application of metal sulfides. The advantages of this system is it particularly useful in wastewater treatment, allowing for the recovery of metal sulfides while cleaning water. Control over pH is vital, as it influences the characteristics and settling properties of the precipitates, optimizing metal recovery and resource utilization. And both strategies present unique benefits and can be selected based on specific operational needs and desired outcomes. Understanding their advantages and challenges help refine the process for better metal sulfide production and resource recovery. Metal sulfides crystallization is also crucial for the application. This specific crystal structure directly affects their performance in advanced applications such as electronics and catalysis. Research indicates that biogenic zinc sulfide exhibits superior crystallinity compared to its biogenic counterpart, suggesting that biological methods may offer inherent advantages in crystal growth and structure. Therefore, focusing on mineral crystallinity through biological production in offline sulfidogenic systems presents a promising approach to enhance metal sulfide quality and achieve resource recovery from waste. It is aligned with a sustainable industry practice. Furthermore, I'd like to share some compelling insights on the application and benefits of biogenic sulfur, particularly in agriculture and environmental remediation. Recent studies have shown that biogenic sulfur can be directly used as a fertilizer with impressive results. For example, in experiments with canola, a common oil-bearing vegetable, the use of biogenic sulfur led to a 50% increase in grain yield. This performance was notably superior to that achieved with commercial elemental sulfur used under similar conditions. This significant increase in yield highlights the potential of biogenic sulfur as a highly effective fertilizer option. Moving on to environmental remediation, specifically in the context of groundwater treatment, the sulfur limestone process is commonly used to drive autotrophic denitrification. However, one of the limitations of this process is the low reaction rate, primarily due to the low solubility of elemental sulfur. This is where biogenic sulfur offers a promising alternative. Due to its hydrophilic nature, biogenic sulfur can accelerate mass transfer, potentially overcoming the drawbacks of low solubility and slow reaction rates seen with elemental sulfur. In conclusion, the use of biogenic sulfur not only enhances agricultural productivity but also improves the efficiency of environmental remediation processes. These applications demonstrate the versatility and potential of biogenic sulfur in addressing both food security through increased agricultural yields and environmental health through more effective groundwater remediation. An innovative approach is to recover and reuse elemental sulfur by leveraging a specific group of bacteria known as chemolithotrophic sulfur oxidizing bacteria, what we can call SOB for short. Elemental sulfur available resource in various industrial processes can be effectively recycled using these specialized bacteria. The process involves SOB using oxygen as an electron acceptor to oxidize sulfide back into elemental sulfur. This biochemical reaction is not only fascinating but also crucial for sustainable practice in industries where sulfur is a key byproduct. The key to achieving effective sulfur oxidation lies in carefully controlling the environment in which these bacteria operate. A fundamental aspect of this control is maintaining the molar ratio of oxygen to sulfide, commonly referred to as the O to S ratio. For optimal results, this OS ratio should be approximately 0.7. So this precise regulation ensures that the sulfur oxidation process is efficient and that the maximum amount of elemental sulfur is recovered for reuse. By adopting such biotechnological processes, industries can reduce waste and enhance their sustainability profile. And in these slides, I'd like to dive into the challenges and strategies involved in maintaining the optimal oxygen to sulfide ratio in bioreactors, particularly focusing on the role of dissolved oxygen control. Maintaining the proper OS ratio is crucial for efficient process operations, especially when dealing with processes like sulfur oxidation in bioreactors. A common strategy employed to achieve this is the control of dissolved oxygen within the reactor. This approach is particularly effective when the reactor operates under a relative stable sulfide concentration, allowing for consistent and predictable reactions. However, controlling dissolved oxygen presents its own set of challenges. According to literature research, one of the main difficulties is the dynamic nature of DO concentrations. As oxygen is continuously consumed during the bioreaction, its concentration in the reactor fluctuates, which can make it challenging to maintain the desired OS ratio consistently. This fluctuation can affect the efficiency of sulfur oxidation process, potentially leading to less than optimal system performance. This dynamic scenario requires robust monitoring and adaptive control systems that can respond in real time to change in oxygen levels, ensuring that the OS ratio remains within the desired range. Implementing such system can significantly improve the stability and efficiency of bioreactor operation, leading to better overall process control and outcomes. And moreover, oxidation reduction potential ORP determined by both sulfide and DO concentration. It is also a more feasible alternative indicator for controlling selective sulfur oxidation. Firstly, let's discuss the role of sulfate-reducing bacteria in hydrogen production, specifically how their hydrogenase activity increases in low sulfur environments during lactic breakdown. In low sulfur setting, sulfate-reducing bacteria show heightened hydrogenase activity, producing hydrogen as a byproduct of lactic decomposition. For example, a study demonstrates that these sulfur vibrio produced hydrogen at a rate of 0.6 millimole per liter per hour when utilizing fomate as the sole electron donor. This rate increased nearly tenfold to 5 millimole per liter per hour using a sparging reactor that maintains low hydrogen partial pressure, optimizing their thermodynamics. Another research identified two main electron transfer pathways in disulfur vibrio. One is direct electron transfer through periplasmic hydrogenase, and the other one is transmembrane electron transfer method. And here, for example, the disulfur vibrio gigas will use the direct periplasmic enzyme pathway, affecting its hydrogen production capacity. For other examples, in bioelectrochemical systems, the disulfur vibrio species can also show the potentials. The disulfur vibrio Wheeler gas, for instance, catalyzed hydrogen production when immobilized on a carbon electrode with a methyl valogen as a redox mediator. All these findings underscore the potential of sulfate-reducing bacteria in hydrogen production. Although the ongoing research and development are needed to refine and scale these processes for broader application. So here, let's see another example, the sulfate-reducing process involving the competition between incomplete and complete oxidizers, particularly in the context of how these bacteria interact with and utilize substrate derived from anaerobic degradation of organic matter. In environments where sulfate-reducing bacteria thrive, there is a notable competition for substrates such as hydrogen and lactate, which are intermediates in the degradation of organic materials. In this scenario, it's typically the incomplete oxidizer that gain the upper hand over complete oxidizers. This dominance is crucial because it steers the metabolic pathway towards incomplete oxidation as the more prevalent method. What does this mean in practical terms? Essentially, when incomplete oxidizer dominate, there is an increase in the production of metabolic intermediates during their processing of these substrates. This leads to some interesting outcomes in terms of the types of compounds these bacteria produce. For instance, some species of disulfur vibrio, when interacting with organics or fatty acids, can produce hydrocarbons ranging from C10 to C25, carbon 10 to carbon 25. This capability is significant because it highlights a potential avenue for biotechnology applications, such as biofuel production, where those hydrocarbons could serve as valuable bio-based chemical resources. Understanding this dynamic and harnessing the capacities of these microorganisms could open up new paths for sustainable chemical production, leveraging the natural metabolic process of bacteria to generate useful products from otherwise waste substrate. let's discuss an advancement in biotechnology regarding the synthesis and the storage of polyhydroxyalkanoates, PHA in short, by sulfate-reducing bacteria in saline water environments. PHA are biodegradable biopolymers and potential eco-friendly substitutes for petroleum-based plastics. Research indicates that certain SRB, especially when cultured in saline condition with benzoate, can accumulate significant amounts of PHAs. For instance, disulfurnamol can achieve PHA content as high as 88% of cell dry matter, a figure competitive with the top commercial PHA producer. Despite promising results, the economic challenges still persist in PHA production, because the production cost can range from 3 to 5 USD per kilogram, using a fed batch process with waste material, which is considerably higher than 1 USD per kilogram cost for conventional plastics. And major expenses include feedstock, aeration, maintaining sterile condition, and PHA extraction. To improve the economic viability, integrating PHA production with processes like wastewater treatment could reduce costs. And in addition, the PHA content varies among sulfate-reducing species, such as Desulfurbacterial, Desulfurococcus, Desulfursacchina, and Desulfurbotulus, with the PHA content ranging from 11% to 43% of cell dry matter. This variability suggests opportunities for strain selection and optimization for better yields. While economic barriers are significant, the environmental benefits and potential cost reduction through integrated process present a promising future for sulfate-reducing bacteria-based PHA production. The pursuit of suitable biopolymers as a viable market alternative continues to be a worthwhile endeavor.